Good afternoon. This is a re-recording of a lecture presented as part of E0318 Topics in Geometric Algorithms. In this lecture, we're going to discuss about the approximate traveling salesman problem using quad trees. The main aim is to present a probabilistic betas which runs in O of n 1 by epsilon log n to the power 1 by epsilon time. Before we present the main algorithm, I'll be presenting a exact algorithm which runs in exponential time, but it lays out the basic tools that we will be using for the uh, main algorithm. So this is going to be a divide and conquer based algorithm. So let us begin, and I'll start with some definitions used in this algorithm. So first, a point set is just a collection of points, right? So it will be used depicted usually as capital P, and it's going to be a subset of R square. So yes, it's important to note that here we are dealing with the Euclidean traveling salesman problem. So that means that all these points are in R square, the real plane, and we're going to be looking at a tour in the real plane. So what is the tour in the real plane? So a tour is just a function such that it starts and ends at the same point. So yeah, so think of this variable that we're giving as the input to be the time. So and as time progresses, we move on the plane and we start and end at the same point. That makes it a tour. We also require that our tour is continuous and piecewise differentiable. So the continuity is for the it basically is telling that there's not going to be any teleporting, right? The path has to be, and the piecewise differentiable means that we can't go too wild. We can't just change direction every second. It is mainly useful for integrability. So it will help us define the length of the tour. So the next thing is what we're going to call a TSP tour. So given a point set P, right, a TSP tour is a tour which has all the points P. So um, so we will be slightly abusive in notation and sometimes use P to describe the path as well. And I mean the path is just going to be, the image of P, or another way of notating it is P of 0, 1, right? So this is going to be the set of all points covered by the tour, right? So we call it a TSP tour, and we will use pi to denote a TSP tour in general, right? So it's a TSP tour pi if the whole point set P is a subset of pi of 0, 1. It is a tour on the plane which covers all these points. That's called a TSP tour. The next thing we care about is the length of a tour. So the length of the tour is the naive idea is the distance traveled. So in general for tour, we're going to show it by two lines on both sides, right? And the length of the tour is going to be the integral from 0 to 1. So you take the derivative of this function p and integrate it from 0 to 1. And that is going to give you the length of the tour. And so this is why we needed piecewise differentiability. So for this derivative to exist, and since it is continuous, we can integrate over this. And the is going to be well defined. Of course, we don't have complete differentiability, we have piecewise differentiability, in which case, we define the integral to be the sum of the integrals over each piece. So the length of the tour is well defined. And of course, in every sane case, which we will have to handle, it is exactly what you would think it is, right? So for example, if you had a bunch of line segments, it is the sum of the lengths of the line segments, right? That is the length of the tour, the total distance traveled. So now that we have these definitions, we can finally define the exact problem that we want to solve, right? So the traveling salesman problem, again, here it helps to say that it is the Euclidean version of the problem. The Euclidean traveling salesman problem says that Given a point set P, we want to find a TSP path pi opt, right, such that for every other TSP path pi, the length of pi is greater than or equal to the length of pi opt. So we want to find this optimal TSP path pi opt such that every other TSP path is greater than or equal to pi opt in length. This is the main problem. So now to solve this using divide and conquer, what we need next is to know what a subproblem looks like. Right? So for divide and conquer, we just define some subproblems and we solve the subproblems, and by assimilating them, we solve the whole problem. That's the whole strategy. Right. So now for the to solve the subproblem, let us see what we need. Right. First, we have a half open rectangle. Right. So it is defined as, so this notation. So in general mathematics, a square bracket tells you that that end is included, and a curled bracket tells you that that end is not included. So this set here, right, a comma b cross c comma d. So what it's going to look like in the real plane is that you have a rectangle here, right? And on the x-axis, this is your A, and this is your B. And on the y-axis, this is your C, and this is your D. And so this two edges of the rectangle are included in the shape, and these two are not, right? So what we'll often do is these sides which are not included, we'll represent them by dotted lines. So this is what our rectangle is going to look like. So points on these boundaries are said to be in the rectangle, but points on these boundaries are said to not be in the rectangle. So this is what a half of a rectangle is. And so A, B, C, D are any real numbers. The next is crossing points, right? So it's a term we're going to use for a finite subset of the boundary of the rectangle. Okay, so that's the next thing, right? Let's also quickly define the boundary of the rectangle. It is just all four line segments together form the boundary, right? So whether it's included in the rectangle or not, all four line segments are included in the boundary of the rectangle. So crossing points is going to be a set K, subset of the boundary. So that's del R, right? And so where we're going to use K is that if you're given a rectangle and we're given, some path, right? Of course, we'll see that a path won't usually look like this if it's a TSP path. But for given any path, the thing is we just care about where this path crosses the rectangle, right? So this is going to be one place where it crosses. This is going to be one place where it crosses. So these 2 points together form K, right? So K is a subset of the boundary wherever the crossings happen. And another thing to note is that since this is a closed tour that we're talking about, K is going to be even. The size of K is always going to be even, right? It's simple. So think about where the tour starts. If it started outside, it has to eventually end outside. So no matter how many times it goes in or out, it has to eventually go back outside. So the total number of intersections is going to be even. Similarly, if the tour started inside, right, and it goes out, in, finally it has to end by coming back in. So it's going to be even. So the number of intersections is always going to be even. So K is going to be an even number. And let's also say that mod K is lesser than T for a fixed constant T, right? So for this subproblem, we are going to have a fixed parameter T, and we're going to say that the number of times that the tour crosses has to be less than T. Yeah. So the next is a permutation of K, right? So yeah. So sigma is going to be a permutation function, and we're going to take the numbers, 1, 2 up to mod K, right? So this is going to be a set of natural numbers from 1 to mod K, and we're going to assign to each number an element of K. So think of it as a bijection from K to itself, but it's a permutation of K. That's simply what it is. And what this permutation tells us is it tells us the order in which these points cross K, the two crosses K. Right. So now, for example, if I had just the set of these 6 points, what I need next is to know that. So let us say I'm starting here and going this way, right? This is going to be 1. This is where the two first crosses. Then this is 2. This is 3. This is 4. This is 5, and finally this is 6. Right. So that is going to be captured by sigma. So so sigma is a function from. So in this case, the mod k is equal to 6, right? Assuming t is a number bigger than 6. So then it's going to be a function from 1 to 6 to k. And so sigma of 3, for example, is going to be this point, which is in k. Sigma of 5 is going to be this point, which is in k, right? So that is what sigma does. It tells you the order in which it passes. So what we want here finally is that given, uh, yeah, yeah. So what we want is that given this rectangle R, and the points on k where it crosses, and the order in which it crosses them. So let's say 1, 2, 3, 4, 5, 6. Okay. It can be as wide. Like as far as the definition goes, we don't care. So we can just abstractify the definition. That's generally, divide and conquer. It's like we don't care what happens in the smaller stages. Finally, we get an answer in the top stage. Right? So now what we want is we want a collection of paths which go like right. Yeah. We want a collection of paths which goes from 1 to 2, 3 to 4, 5 to 6, such that every point in a point set which lies inside this rectangle is covered by these paths. Okay. Yeah. So we are going to have mod k by 2 paths, right? Because each path goes from one of the points to the other. So, and to be particular, each point goes from the sigma of 2i minus 1 to sigma of 2i. So the ith path goes from here to here, and they're going to be mod k by 2 such paths. So in general, like just as a notation, we're going to call this, just to be k2i minus 1. And so we're going to make k an indexed set, basically. Indexed by sigma. And the next thing we want is that, so the point set which lies inside the rectangle, right? So let's call this not string of yeah. So whichever points from the point set lie inside a rectangle R, right? So this is the rectangle R. Has to be a subset of the union of these paths. So let's go name to the paths as well, right? So let's just call them pi I, right? Pi I goes from k to I minus 1 to k to I. And so this is just going to give us, a collection pi I is equal to 1 to mod k by 2. And so finally, the union over this, so I is equal to 1 to mod k by 2 pi I, right? Has to contain all the points which lie inside the rectangle. And we want to do this such that the sum of lengths of these paths is minimized. So this is the goal of our subproblem. And how does this help with solving our problem? So initially we are given a certain point set, right? And what we want to do with this point set is that, so first we take the bounding box of this point set, right? And you can think of this as also as a subproblem, except that here we want to do, right? And then what we do is we draw an arbitrary line and we cut the whole space into 2. And then we decide where it's going, where the tour is going to cross this line. So for example, in this case, this was the tour. Yeah, okay, right. And so the order is then going to be 1, 2, 3, 4, right? So let us say this was the tour. And so then that we want to find. So then what we do is that we break it into two subproblems by drawing this line. And then on these two rectangles, we put these 4 points and give it this order 1, 2, 3, 4, and tell it to find the shortest paths. So this guy is going to find this and this. And then for this problem, the solution is going to be this and this. And so then by taking the union of the two solutions, we get a path. And so for here also, we find this solution for this guy by breaking it into two parts and then solving these two. And then we solve that by breaking that into two parts, the whole divide and conquer thing. But this is the idea that this is what we want to do. Okay. So now to do this, yeah. So yes. Some trouble with my mouse. Just yeah. Fine. It's good enough. Yeah. So now to do this, let's get into some definitions, right? So what are the cutting lines? So the cutting lines is going to be script L of P. So given the points at P, right, we want to find the cutting lines, and this is going to be the set of all vertical and horizontal lines that pass through points in P. Okay. So yeah. So now like if I'm given my R2, right, and I have a point here. So what I'm saying is, so this is my point P. Okay. Now capital V of P is just the vertical line passing through P. Capital H of P is just the horizontal line passing through P. Right. And so what I'm saying is that if this is my point set capital P, right, this is my point set here, then what I'm going to do is for each of these points in my point set, I'm going to draw the vertical lines. I'm going to draw the horizontal lines, right? And take the union of all these lines that I just drew and call that L. So it's the union of all the vertical lines passing through the points and the horizontal lines passing through. So these are called my cutting lines. The next thing is possible edges. Okay. So this is a very intuitive concept. The idea of, so now, what is a possible edge for my optimal TSP path, right? So because we are in the Euclidean method, the shortest line between 2 points is the straight line. The shortest path between any 2 points is a straight line. So now, if I had, again, so I'll just redraw the points up there. Yeah, I don't need to erase that. Just yeah, space is enough. Let's go a bit up and redraw it. Yeah. So if you have the space, and these are some points that we have, right? So after I decide that the order in which I'm going to visit these points, all I need to do after that is draw straight lines between them, right? So there's no point having a squiggly line here. Basically, the straight line is always better. So in a sense, the whole problem is finding the order in which we need to visit these points. And once we do that, we just draw straight lines between them, and that is going to give me the optimal path. So I mean, and that is true because that path is going to be the shortest tour, which visits all those points in that order. And we decided that that is the shortest, that is the best order to visit them in. So it is going to be that. So now that means that whatever our tour finally is, because a priori we don't know the best order in which to visit all the points. But whatever the tour that is, it is only going to have edges, which are straight lines between points. So then if we just consider straight lines between every single pair of points, right? All of these lines, all of these lines, all of these lines, and we just consider all of them, then our final tour is just going to have a subset of these lines, right? So our possible edges, right, we're going to call it E, is just the union where all I comma j belonging to P, Eij. And Eij is the straight line between I and j, right? So Eij is the straight line from I to j. So yes, I hope the idea is clear that whatever a final optimal TSP tour is, it is only going to have straight lines between points. So let us call the set of all straight lines between points to be E, so that we only need to take points between lines from E. The next idea is the idea of a rectilinear binary space partition. Okay, so what is this? So let us look at this image again, right? So what we want to do here, um, so what we did here is that we had a problem, right? So let's draw that here, say. So we had a bounding box of the points at P, and then we have the points at P itself. Yeah. And now what we want to do is we want to draw some line that splits this and gives us two subproblems. To solve this right subproblem, we want to split this. To solve this subproblem, we split this again. And now these two are single points here. So we solve. So we take that as the base case. You know, whenever there's a single point in a rectangle, that's our base case, and we just solve it by brute force. And then so here next I draw this line, and then this still has two, so I draw this line. And over here again, same thing on this side as well. I draw this line first, and then this, and then this, and then this, and finally this. Okay, right? So now what you have here is that you have a bunch of rectangles, each of them having exactly 1 point, right? And we did this by iteratively cutting our rectangles. So the first cut was this one, which gave me two rectangles. And then this rectangle again I cut here, and then which gave me two rectangles again. And then this rectangle I cut, and then this. So basically I just kept iteratively cutting rectangles to get a final set of small rectangles which contain 1 point each. So this is my idea for ternary binary space partition. It's basically the subproblems that I'm going to visit on the way while reaching the base case. So we can define a ternary binary space partition as a family of rectangles, right? Let's call it script R maybe. Is that, yeah, sure, it's a good way to draw script R. Let's stick with this. Right? So it's going to be a family of rectangles script R, such that if I have two rectangles R, S in script R, whose intersection is non-empty, then either R is a subset of S or S is a subset of R. Okay, so think of it this way. So this was our rectangle that we had, and then we split it using this line, right? So now this rectangle, laser pointer for this right now. Yeah. So now this rectangle that we have has an obvious intersection with this bigger rectangle because it is a subset. But what this first axiom says is that is the only possible relation where they are where they intersect each other. If two rectangles intersect each other, then that's only because one of them came from the other as a subset. So this, for example, cannot have any intersection with this guy. Right? So that's what the first axiom tells us, that if two rectangles intersect, then one of them is a subset of the other. The next thing is that there will be no rectangle which doesn't have any points in it, right? So every single rectangle that I consider is going to have at least 1 point from the points that in it, right? So, okay, so this rectangular binary space partition, this my big set R, is going to have all these intermediate rectangles as well, right? So it's not just this smallest set of rectangles. Starting from the complete big rectangle, right? This one. And then I'm going to have, this as one rectangle, and then this as one rectangle. And then I cut this again. So this is also going to be one rectangle. This is also going to be one rectangle. This is also this, right? So all of these are going to be rectangles in my binaries, in my RBSP. Okay. Okay, so that's my second one, which every single rectangle has to have at least 1 point in it. I will never cut and create an empty rectangle. So the next one tells me that, so if I have a rectangle R, which is a subset of S, so if R and S intersect, that tells me that one of them is a subset of the other. Let's say that R is a subset of S, right? Then whatever is the difference between R and S has to be the union of other rectangles in the RBSP itself. So now let us say, for example, that this is my S and this is my R, and R is a subset of S. So S minus R then is going to be this area, which itself is a rectangle, right? But let's think of a bigger case. So this is my S and this is my R, right? Then you can see that S minus R itself is not a rectangle, but it is going to be the union of some rectangle. So for example, we can take this rectangle and this rectangle, and their union is going to be S minus R. So what this tells me is that to reach from S to R, right? So since R is a subset of S, to go from S to R, I can only do it by cutting away a rectangle step by step, right? So that's exactly the definition I wanted, right? Right, to cutting away. So I started at S, I cut away this rectangle, I was left with this much. Then I cut away this rectangle, and I finally reached R. So the union of these two rectangles is exactly going to be S minus R, and that is what this tells me. And the last one is for every point in the point set, this RBSP zeroes in on the points. So that is the main goal that we want of this RBSP, that it starts from the whole big rectangle, and it keeps cutting rectangles until we reach our base cases, right? Which are that there's only a single point inside the rectangle. So this is telling me that I want this set of system of rectangles to be such that for every single point in the system, it's going to have there is going to be some rectangle which has only this point in the system. Right? So this completely defines the this notion that I wanted. So this is going to be a working definition of an RBSP. So just think of it as iteratively cutting to get singletons, right? The singletons are going to be our base cases. So finally, you can see that in our divide and conquer, what we want to do is we want to cut down along an RBSP until we reach our base case, solve the base case, and then assimilate them to become bigger. Now, the next definition is a notion unique to this algorithm. It's called a T-friendly RBSP, right? So now let us pick our favorite tour on this point set. For example, let us say that this is going to be the tour I pick on this point set. Okay, straight lines between the points. That now an RBSP is said to be T-friendly if no rectangle in the RBSP intersects the tour more than T times. So I'll say that again. So we look at this tour, right? And now, for example, look at this rectangle, right? How many times does it intersect the tour? Twice, here and here. Let's take a bigger rectangle. How many times does this rectangle intersect? Twice, here and here, right? And you see that for any rectangle, the most times it intersects is sure, this is randomly drawn. It might be probably this one, which no. Let's see. Oh, I see this guy intersects 4 times, right? So 1, 2, 3, and 4. Yeah, so 4 intersections on this rectangle. And that is probably the most times that any rectangle intersects, right? And you don't need to consider the small ones as well. You can consider even the big ones, and this also intersects twice, right? Every rectangle in the RBSP intersects this tour at most twice. So what I would say then is that given a tour P, P I used for points, so let's just use pi, even though it's going to be a TSP tour. Given a tour pi, the RBSP R is said to be T-friendly if for all R in the RBSP, pi intersection, okay, it is not R itself. The number of times it intersects the boundary of R is less than equal to P. So for every rectangle in the RBSP, it is intersected lesser than R times, less than or equal to T times, right? So this is intersected. So as an example, so for this purple pi that I have drawn and this RBSP, right, it is 4 friendly, but it is not, for example, 2 friendly, because there is one rectangle right here who intersects more than twice. Now, with that definition, we can tell the main theorem of this section, which is that for a constant t, if a point set P admits a minimum TSP2 pi opt and a RBSP R that is T friendly, also, yeah, this guy is how LaTeX treats this guy. So this is the symbol for an RBSP. Yeah, that is T friendly with pi opt. Then we can find pi opt in time n to the power of t. So what does this say? So okay, so one thing you notice is that pi opt need not be unique, right? So we just said less than equal to. So there can be two distinct paths, two distinct TSP2s of the same length. So then they're both going to be pi opt. I mean, either of them is a candidate pi opt, right? But if points at P pi opt and an RBSP such that R is T friendly for pi opt, then we can find pi opt in time into the power of T, right? So this basically tells me that I can exactly solve the Euclidean traveling salesman problem if there is an optimal path tool which is T friendly with some RBSP of the point set. So let's just check how we're doing on time. Okay, so this should be a good time to cut off this video, I guess. So in the next video, we'll get into the exact algorithm, and then we'll discuss the correctness and the runtime of that algorithm to show that this statement is in fact true. Thank you.